This is AI Talks, your regular monthly jab of highly concentrated machine learning use and know-hows. 100% informative and exciting stories on the bleeding edge of ML tools from SoftServe. My name's Daniel Einor. I'm happy to be your regular host of tonight's AI Talks. Yay! Just a small reminder, in case you would like to ask a question to our speaker, we do have a chat box, so keep your notes and questions out there, and I will read them out loud later after the talk. All right. It's going to be an interesting topic today. You know, in the world of data and all the spectra of parameters, features, metrics, numbers, counts, coefficients, values, indices, estimates, KPIs, calculations, rates, and frequencies, we are constantly struggling to find that single value and only number, that philosopher's stone of statistics that will help us answer all the questions. Many academic researchers and industry professionals have been delegating their decision-making process onto this notorious p-value. What it is and why is it notorious? Let me invite our colleague, data scientist, our star, Karol Kawalerczyk. Thank you, Karol, for preparing this talk. I'm excited that we're gonna break the ice on the p-value. The stage is yours. I'm stopping sharing and go ahead and share a screen.
Okay, let me share my screen and I'll go ahead with the talk. Okay. Hi, everyone. I'm happy to be here as well. I'll start with a little self-introduction. So I am a data scientist at SoftServe. I've joined the company in January. I'm in the data science field for already 5 years. I used to work in mostly R&D departments, some form of R&D departments, because they were more or less official that. And due to my university degree, which is biomedical engineering, I tried to stick mostly around biomedical related projects with more or less success. Like life can be not predictable so much. What I would like to talk to you today is about the p-values. So we will start with introducing what is actually p-value for, so that we all have a common understanding of it. I will ask you to join a quick quiz. It consists of 4 p-value statements that I will ask you to answer true or false. We will see later what is the general knowledge about the p-value. They might be a bit tricky. Then we will try to lay common grounds for p-value understanding and statistical models, statistical testing. Like we will try to cover the basic topics over there. And we will finish with some tips and guidelines of how not to use it, how to understand it, how to interpret it. Okay, so what is p-value actually good for? In general, p-value is here to help you make informed business decisions. So let's ponder on it a bit. It's to make the decisions. It's to make business decisions. It's to make informed decisions. And the most important part is to help you make the decisions. So the p-value, after all, isn't a tool for making decisions for you. It's here to help you make the decisions. And a couple of examples where we can use it. The first one would be in the e-commerce. We would like to know if a new marketing campaign actually brings more customers to the company. And you run A/B tests on a small samples of customers. What you end up in general is usually not a single number, but it's more like of a distributions. So it's not always easy to tell whether the value of a new website brings actually some improvement or not. This is where we would like to do a hypothesis testing. And the p-value is like, in the end, a single number that you usually refer to. And I'm going to talk later about that maybe it should not be the single value that you base on. Another example, like very, very relevant, I believe that p-value is the most common in this branch of industry. These are the clinical tests. It's all about connected to medicaments, about drug testing, about new treatments testing. And you would use it if you would like to know whether a new drug actually has a higher effectiveness than the old one. After collecting the data, running an experiment, what you want to do is to run a test, is to test your hypothesis with a statistical test, and in the end, take a look at the p-value. User profiling. We deal with many using profiling applications. You want to know if those two, if some two segments of users you mapped are actually different in terms of your business values. For example, you want to measure if some group of people, for example, diverse by age, spend more money. And in order to do that, you would use the statistical testing over here. And last but not least, recommendation systems. This is a pure machine learning application, I would say. And in the end, when you deal with the recommendation systems, it's really hard to develop a useful online metric for recommendation systems. I have never met one that is really, really reliable. So the best shot that you can get is A/B tests once again, and even ABC tests so that you have some referral group. And you want to test whether the new architecture or some improvement in parameters brings actually the change. Well, in the end, you run it on live users and you do A/B tests. And in the end, you look at the p-value. This is where you use it. It's here to help you make the decision whether all these cases matter. I have a little bit of personal motivation about p-value, and it's kind of because I wasn't actually good at it. So I was basically forced to learn it because I never was sure whether I used it the right way. So the first time I found the p-value, or I learned about the p-value, was at my studies during the statistical classes, and I was introduced with a simple algorithm to make decisions. The problem is that I learned it. It went pretty smoothly. It was quite easy to me. I followed the same algorithm through the exams, and I ended.
Извинявай, сега чуваш ли?
I'm sorry. All right, I'll just go on. Okay, so coming back, I brainlessly followed an algorithm through the studies. I ended up with an A from statistics, and I was pretty proud of it. Like, wow, this is easy. This is my best grade in the studies. But what could go wrong? When it came to real life and I had to use it, I was like almost never sure whether I'm using it the right way. Like, it seemed to have so many little things that you need to care about that I was always afraid to say for 100% something. And I also noticed that my far more experienced colleagues at work also hesitated about it. And then I found that there are plenty of publications about the p-value misinterpretations. It got me calm a little, so I thought like, hey, you cannot say something for 100%, maybe it should be that way. And that's a fact, like p-value is not a simple concept. And in the end, a straightforward tool to decide whether the research is valuable or not became a very ambiguous one and not giving you much confidence about the research conclusions. So I'm still struggling.
Извиняй, чакай, че пак съм натиснал микрофона.
All right, thank you. Sorry about that. Okay, I'm still struggling, not to tell a lie, when I'm interpreting a p-value, and I have a feeling that my speaking speed is like literally 2 words per minute. And it's just one sentence, it brings a lot of confusion, and at this point, words really matter. The problem in our general world is that a lot of research is not reproducible and quite often due to poor data. And that should be included in a statistical analysis. My next motivation is a quite silly one, I would say, is I have a feeling sometimes that my mother thinks that I'm a flat earther. My mother is a person that really likes to read a lot of stuff in the internet. They are usually quite good mass media articles, I would say, but still, even though they are proven to be very popular, they are not always right. And one time I had my mother came to me and said, like, I'm introducing eating 2 olives per day right now. The researchers said that if you do that, you won't get cancer. And I'm like, okay, my first reaction is more like someone discovered a secret how to stay healthy, like probably pharmaceutical industry hates him. That's too good to be true. And what is actually the situation is that there's a really long way from a research to journal, to scientific journal, and then to mass media. Like there's a lot of room for error on the way. Sometimes it reminds me a bit about child's play. I'm not sure whether that's popular just in Poland or in all other countries, but you have a children sitting in a line. The first person in the line figures out a message. It passes through the next person, who passes it through the next person, who passes it to the next person. And while it reaches the end, in the end, you want to compare the message from the very end to the message from the very beginning. I'm not sure I ever took part in a play like that figure out the original message through the whole pipeline. And that's how I think it works. And the problem is that research papers are actually far from giving strong statements that we read in like clickbaiting articles that we have. And they might not be totally wrong. They just cherry pick the stuff that people want to hear. And let's try to be aware about it. Like, I remember a situation also that I was always told when I was small that I should drink a lot of milk, and maybe butter is really bad for you. You should switch to margarine. And literally 5 or 10 years later, I learned that, well, drinking so much milk is not really that good for you. And margarine is actually the worst alternative for your bread. You should switch back to butter. So I thought, like, how is that possible? What happens over there? And while it's like a general problem that has been many factors, what we can care about is actually the statistical analysis, and that we have effect on of how we understand it, whether we interpret it right or not. My first message to you would be that p-value should not be simplified, and this fact should be stressed more. It's not supposed to be a simple concept. It's not to be a straightforward decision-making tool. It's just to provide you additional information that is valuable, but it's not final. Let's have a short quiz. I will ask you to answer 4 questions, and let's have 2 minutes for it. I hope that's enough.
Yeah, you should see the pop-up window with the quiz. Let me know if you don't.
Also, let us know if you need a minute more or something, because the questions are kind of long, but they should be understandable.
Sorry, I cannot share the music over here because now that's not me sharing the screen. And I don't want this to be a minute of silence, you know. Oh, yeah, if you please. If you please. You can do something AI generated. People are discussing that music we heard before it was AI generated or not. We got some interesting results here, though.
Okay.
All right, I will allow 40 more seconds. All right, 10 seconds. Don't worry if you don't know the right answer. Karol will cover all of them all.
That's correct.
Yeah. All right.
Is that it?
10,
Do we have it?
5, 4, 3, 2, 1. Last click. Okay, thank you all. I'm closing the poll and let you all see the results. We almost got a like 60 to 40, 50-50 split
Nice.
on most answers. And
Okay.
many of our audience members chose true to all the questions. All right, go ahead.
Okay, so I think I've proven my first point that it's not an easy concept since your answers are split almost 50-50, I would say. And the correct answers to all of these statements is false. All of them are false. They are all misconceptions. And some of them are tricky, so you might have got caught on some tricky part of it, but we will go through all of them once we introduce like how we should understand p-value. Thank you for the participation in the quiz. So let's go with what we think model is. So what usually people think about the model is some mathematical equation that somehow illustrates of how we perceive the world. So it's a mathematical approximation of how the world works, basically. And that's true. That's true for machine learning. That's true for statistics. But it's also not a complete answer, I would say. In terms of statistical testing, it's very good to think of a model as a whole way of thinking, as a whole process, as a whole way of thinking, as a whole way of how we perceive the problem, how we perceive the world. So it doesn't only include the mathematical equation, it doesn't only include the mathematical distribution, like the statistical distribution of some real world phenomena. It also includes the data analysis process, all of the assumptions that we make on the way. It involves the way we collect the data. It involves business context, and it involves our common sense. And every assumption, every single, even small assumption that we make on the way, if we pack that into a single funnel, we get a statistical model. And this is a very helpful way to think about it when it comes to statistical testing. I'll probably repeat it like 100 more times because this is one of the takeout lessons that I would like to provide you, to think about the statistical model about something much more than equations. I want to provide you with an example assumption. So we have something like genome-wide association studies, and it's a database. It contains a database, a catalog of genomic data. And let's say that we would like to run an experiment on it. The majority of this data comes from European people, while the minorities are very small over here. So it's highly imbalanced data set. The assumption that we make, if we, for example, don't see the diagram, because if we see the diagram, it's quite obvious that it's imbalanced, that we sample uniformly from this database. And we run an experiment. And we run some experiment containing HIV resistance. And the results that we get, we can interpret the following way. The mutations affecting HIV resistance found in Hispanics less often than in Europeans. That can be really misleading because it's quite obvious for us when we see the diagram that if you draw the sample uniformly, you get more Europeans than Hispanic. And if you compare the numbers instead of, for example, percentages of specific group of people, you get wrong answer because obviously you're going to get that Hispanic tends to be less HIV resistant in that form. The study is not conclusive because of the bias in the initial data set. And this is quite basic error that you can make in machine learning and all that stuff. But it also is true in statistics, and it's just an example assumption that should be part of our thinking when we talk about the test hypothesis. So what actually is a hypothesis? Let's start with an example. So we have the picture where we have two plants. Each is enlightened by a different color of light. And we set a hypothesis. The plant growth is not affected by light color. And this is our hypothesis. So hypothesis is kind of assumption that a particular effect has a predictable value. And if that value is 0, so there is no effect, that's what we usually test, is this hypothesis is called null hypothesis. You can also hypothesize about different things and usually a range of values. And for example, in case of our plants and lights, it would be that an example hypothesis would be yellow light affects growth speed and increases it by 1 to 2 months. And that could also be a hypothesis. So the first problem that we meet in statistical teaching and practice is that there's too much focus on null hypothesis. Sometimes it's not enough. And sometimes if you test that there is no effect and you reject it, that's not enough to say that there is effect. That's not enough to say that there is an effect in a specific direction, in a specific range. Maybe you should think about testing more than null hypothesis. This is one of the things that maybe you should consider. And this is very strongly connected to the first hypothesis. And this is the biggest fallacy, I would say, that you can get about the p-value and statistical analysis. So does the conventional statistical analysis refer to hypothesis probability at all? It does not. The thing is that you cannot talk about the probabilities in this case, like about the probabilities of hypothesis. This is the crucial part. The goal of statistical analysis is to provide an evaluation of certainty, some form of certainty. There is no hypothesis over there. So this is going to be a bit of hard sentence, I would say. It refers to quantities that are hypothetical frequencies of data patterns under assumed model. Let's think about what it means actually. So the first and one of the most important parts is that the hypothesis comes first, and not only the hypothesis, assumed model. So our whole way of thinking in statistical testing comes first. We assume it's true, and then we check that in case that is true, we run an experiment, we get the data, and we see how that data fits our model. And we are talking here about more of a hypothetical frequencies. Hypothetical because we assume that our way of thinking is true. So it's kind of hypothesis already. And the frequencies here, that statistical analysis talks about the frequencies in terms, we get this data from our experiment, we have our model, and if our model is true, every single assumption of it, then how often would we get this data? And based on this kind of sentence, we make decisions on whether reject our model or not reject our model. So we say that we are rejecting hypothesis, but that's in case that we are sure about all of the other our assumptions. So what is a test statistic and a p-value? So let's have some definitions of it. And let's start with an example. So we have our null hypothesis that people spend on average $100 a day in a shoe store. We collect the data from 100 days from a picked shoe store, and we find out that the mean value of our sample is $125. So where does the test statistic fit here and our p-value? The test statistic is basically a tool to calculate the distance between the data and model predictions. So $100, average $100 is our model. We believe that that's how the world works, and we want to verify it. And then we get $125 from our data. It's our observation from an experiment. And the simplest test statistic over here would be a difference between these two. So if we take out one from the other, we get $25, and this is our test statistic. And what is a p-value? We will give a very formal definition over here that we will explain a bit later and break it down to many, many cases. And so it is a probability of obtaining results at least x extreme as the results actually observed by chosen test statistic if every single model assumption were correct, including the test hypothesis. So there are two crucial parts about this definition. The first one is at least x at least as extreme. It's often missed, it's often not thought about, but it makes you think a bit different way about your hypothesis. And the second part is if every single model assumption were correct. The definition that you can find in many statistical books usually includes only the test hypothesis. So it says that it is a probability, if the test hypothesis is correct. That's not enough. Every single assumption of our model has to be correct. So our whole way of thinking about it, we need to be sure that the way we collected the data is correct. We need to be sure that the assumptions that we made on the way are correct. We need to be sure that the way we analyze the data, our pick of hypothesis, our pick of methods is correct, that our even way of selecting results is fine. And only if this case, the p-value holds for its definition. So then it becomes the probability of getting this data. The conclusion from the data we collected, so we are going back to our example, is that assuming that null hypothesis is true and all of the other assumptions, there is a chance equal to p-value, and here's where p-value fits, that we get this or more extreme result. It might be not yet clear to you how it looks like, but let's go to a little picture. So what can we see here? We have a plot where on the y-axis, we have a probability of getting an observation. And then on the x-axis, we have a set of possible results. The hypothesis that we have is a blue curve that we have over here. And it basically tells us how probable it is to get the data under our hypothesis and under our statistical model. Going back to our example, this is the place where our $100 would be. We assume that people spend on average $100. So this is the most probable event in our world. But what we get is $125 that fits somewhere over here. And what is a p-value? Here we go back to the definition that is the probability of getting this value or more extreme. So it's basically the area under this curve. The p-value talks about this value, but it also talks about the values that are less probable on our distribution. And notice one thing, it not only like the tests and the p-value divides into one-tailed and two-tailed. The one-tailed tests you want to do if you're interested in one direction. So in this case, it would be if we would like to have an alternative hypothesis if people spend more than $100. But the usual p-value is two-tailed, and it talks only whether people spend on average $100, and we want to reject it. So it also talks about events of the same probability or higher probability or less or even lesser probability. So it doesn't talk only about this part of the hypothesis. It also talks about this part of the hypothesis. So when we have a p-value, for example, 0.05, it tells us about the frequency of getting data that says it's $125 or 123 or 100 or 150 or 200, etc., but also about the negative values, like the one from the other part of our distribution. So also about the $75, about $65 and lower. This is very important to remember about it when we are using two-tailed tests. So we already know what p-value is not. We already know what is the formal definition of a p-value. And from the misconceptions, we know what we shouldn't say about the p-value. So what can we actually say about the p-value? P-value can be viewed as a continuous measure of compatibility between the data and the entire model. So it's safer to say than its probability, because it's probability at best if our whole model, whole statistical model, whole way of thinking about real world phenomena that we are trying to test is true, then it can be probability. But in the other cases, it's just a measure of how compatible our data is to our model. So basically, how well model fits our data. And that's all. You cannot say that it's a probability of receiving this hypothesis. You cannot say that this is a probability of this hypothesis being true, etc., etc. It's not about the hypothesis, it's about the data and about how frequent it can happen when you assume your model. The smaller the p-value, the more unusual the data would be, once again, if every single assumption were correct. But very small p-value won't tell us which assumption is incorrect. So if we have a small p-value, it doesn't tell us that, hey, this hypothesis is wrong. No, it can say that this hypothesis is wrong. It can say that we violated the study protocols, or that it was selected for presentation because of its small size. That's quite often in research. And we don't know which one of these. All we know is that something's fishy about our hypothesis. That's all it gives us. And the same goes for large p-value. Large p-value brings us some information that, okay, we cannot reject this hypothesis and nothing more. It doesn't tell us that this hypothesis is correct. It doesn't tell us which assumptions of our hypothesis is correct. It just tells us, hey, basically there's nothing you can say about it. There's something you cannot say about it. So you can't reject this hypothesis. And that's all. Let's go to the first p-value misconception. So this was one of the questions. The p-value is the probability that the test hypothesis is true. For example, if a test of the null hypothesis gave p0.01, the null hypothesis has only 1% chance of being true. Instead, if instead it gave p0.4, the null hypothesis has a 40% of being true. What does it say? It basically represents a situation when we have the data, we pick the null hypothesis, we run our hypothesis test, and we treat the p-value as a measure of our hypothesis, being true. That is wrong. Let's think about it in terms of testing drugs. So we assume you are a research scientist. You test new drugs' efficiency compared to the old drug. New drug may have some serious side effects. So the decision of introducing the new cure has some consequences, and it needs to cause more benefits than harm. You run a clinical trial, you collect many patients, and then you set the null hypothesis so that the new drug has no improvement over the old drug, and you get p0.01, let's say. So it's 1% in terms of if it was the probability. And the effect size positive. So we already know that the data gave us the result that, okay, not only your original hypothesis might not be true, also the effect size is positive. So this drug is better in these terms. You cannot say that the probability of this hypothesis being true is 1%. And why is that? Like, when you think about the p-value in a correct way, there is no place for probabilities. What does it mean even that a hypothesis has some percentage of being correct? Like the hypothesis is either right or wrong. You can not be sure about what to say, but you cannot really measure how true is the hypothesis. Maybe it means, for example, when you have the data that 1 out of 20 people fail to notice the improvement, but that's already talking about something different than probability. The whole thing here is that what we do, and what's the proper way to think about this misconception, is that we have a data, we assume that our null hypothesis is true. So before we even run the experiment, we give 100% chance that this hypothesis is true. We measure the distance between the data and the model, and then from the experiment and from the experiment data, we see whether our observations in the experiment fit our hypothesis. And that's all. We cannot talk about the probability. If you, like, let's go to the outcome of it. If someone offers you a probability of hypothesis, you should be on your guard. Like, it's impossible to deliver the hypothesis from pure conventional statistical analysis. There are some mathematical methods to talk about the probability, but they are not so popular yet. It's connected to Bayesian statistics, and it's not connected to the p-values. P-value is more about a frequency of getting the data under our statistical model. It's quite complex, but it's very different from the probability of hypothesis. Let's go to the second misconception. So next question was, a large p-value is evidence in favor of the test hypothesis. That's wrong. Let's think about it in this way. I will use one-tailed p-value test. And let's talk one more time about the drugs and comparing different drugs. Let's say that we want to test whether the new drug works better in 50%. Let's say then that, for example, it cures 50% more people, it works 50% quicker, and so on. And we get the result from our experiment that, hey, you get 40%. When we take one-tailed p-value test, we get p equal to 0.6. Well, and that doesn't confirm our test hypothesis. That is not in favor of our test hypothesis. Why is that? That is because if we, for example, have any other hypothesis that will bring us the p-value greater than 0.6, then this hypothesis would be already better. And any p-value that is not 1 implies that there is somewhere hypothesis that fits our data better, in a more perfect way, I would say. And even when it is 1, it doesn't mean that it's the only hypothesis that can get 1. So for example, if you do one-tailed p-test, that our drug works 100% more, better in some way, then 40% would be here. If you take the p-value, one-tailed p-value, of course. And of course, this example maybe it's not the best, because who would use the one-tailed p-value and test the 100% here? But it's just to show you that you cannot trust just the p-value. So even though the p-value might be big, it's not in favor of the test hypothesis. All you can do is, we can say that the large p-value is not the evidence against the hypothesis. It's not the same as evidence in favor. And here comes the probability of hypothesis once again. So the probability works that if we have a binary situation and we have 40% chance of one thing happening, then we have 1 minus the probability for the other thing to happen. So we get 40% chance for the first event to occur, and we get 60% for another event to occur. This is why it's not like the probability. Even though you reject one hypothesis, you cannot confirm the other. All it says is that hypothesis in favor, okay, what you can say about it is that hypothesis with a higher p-value is in favor with relation to the other one. So this hypothesis would be kind of better than this one. But a definitive conclusion of no association cannot be deduced from p-value, no matter how large. What we can say that what is wrong with some amount of confidence, but we can't say what's right. A large p-value often indicates that only that the data are incapable of discriminating among many competing hypotheses. So here comes your domain knowledge, and you need to support yourself with your domain knowledge, business knowledge to make decisions. You just can reject the hypothesis, that's all. And the takeout lesson from this misconception would be large p-value does not give confidence in a hypothesis. That's all you have to remember. Why is that? We just went in a little bit deeper into that, and you can ponder about it like a lot longer, but this is the clue from it. That's all you need to remember. The third misconception is The p-value is the chance of our data occurring if the test hypothesis is true. For example, if p equals 0.01, it means that the observed association would occur only 5% of the time under the test hypothesis. And this was the one that was tricky because it concerns the first part of our definition. Let's bring the example. So for example, you want to know whether the new website design brings more customer. And you set the null hypothesis that it doesn't have any effect. The experiment brings the results that for example, the original web page brings 23% of customers, of all of your shop customers. So 23% of users actually visit the website. And the new website is visited by 37%. And what the misconception says in this case, here's our hypothesis. And if there is 5%, if we treat it the way that only 5% of this data, the results from this experiment would occur under this hypothesis, then we get this picture. We get a small thin line over here where our values are. And what we already know from it doesn't match the definition of a p-value. What we actually need is this part. So first, the p-value, this probability of 5%, if our data is correct, talks about getting the experiment results of 37% or more. We can get the 37%, we can get the 50%, we can get the 60%. But we can also get under the same probability the values of 9% and lower. So the web page with the same probability might actually occur to be worse. And maybe it doesn't change our business decision in this case, but it certainly changes the way about how we read the p-value over here. Remember that the p-value refers not only to what is observed, but also to more extreme values. And this is the first bolded part in our definition. This is what you should keep in mind, that this is the original p-value definition, and it doesn't talk about the probability of exact value. It's not a point estimate. This is the take-out lesson. So the p-value is not the point estimate. It doesn't provide you the probability of getting the exact statistics. It provides you with the probability of getting these statistics and more extreme. And extremity is measured in some way. In our example, it was measured in probability. So of getting this value and less probable. And the last misconception. When the same hypothesis is tested in different studies and none or minority of the tests are statistically significant, so let's take that all are above the p-value 0.05, the overall evidence supports the hypothesis. And okay, I've talked already about how p-value cannot support the hypothesis, so this is wrong just because of that. This is one of the reasons, I would say, but not only. Like, let's even skip that it shouldn't confirm. If you have some different experiments, so this is what the misconception says to you. Let's assume that you have 4 experiments. Let's say you test the recommendation systems with A/B tests 4 times, 5 times, and you get 4 times insignificant result. So you cannot actually reject the null hypothesis that it doesn't bring any value. You need to consider it. So even though that one study is significant, you would, according to this misconception, just, yeah, okay, this recommendation system is no good because the majority concluded it. So there is a tendency to overestimate the power of the most research. And the fact is that this is not a proper way to combine your experiments, to combine your research. If you get the p-values from different experiments testing the same thing in the same process, there is a way to combine it. And this way is called the Fisher formula. So after you get the p-values from your experiment and you want to combine them into one, you put it into something that's called Fisher formula. And when you combine it in a proper way, it might actually occur that, for example, if you got 5 studies that have 0.1 p-value, and you combine it in a proper way, you get 0.01 p-value. So you get a significant result. And how does that work? So let's think about it. Let's assume that your null hypothesis is true. You run the same study 5 times. And from each of the studies, you get 0.1. What does it mean? The p-value tells you that if your hypothesis is true, the one that you would, according to misconception, not reject, then there is a 10% chance that you would get this data. So you're running your experiment 5 times, and every time you get that there's 10% chance that you would get this data. Already that doesn't really work. You should get different p-values. So remember that there is a proper formula for combining p-values, and then you should use it if you're running your experiments many times and want to bring one conclusive result. Do not overestimate majority of experiments. Combine them in a proper way. This is a takeout lesson from that. Let's go back to statistical model. Let me repeat it one more time. Statistical model, it's much, much more than equations. And we know that there are tests for goodness of model fit. We can get a mathematical way to check whether our model works good in terms of model as mathematical equation, how well it fits our data. But if we take the statistical model as a whole, so for example, picking the data in a proper way, there are no tests that tell us whether the random sampling assumption was fulfilled. We don't know that. In order to follow this assumption, we need to read through the whole process of running an experiment. We need to run through the whole research and use our common sense whether that was done the proper way. And that really affects the p-value over here. The analysis might be guided towards finding significance or non-significance, and that's happening a lot in the research world for various of reasons. It might happen because scientific journal accepts only the significant results. It may happen because we want to impress the client so much that we are doing something like cherry picking, and you should be wary not to do that. There are situations where you really shouldn't dive too deep into your research, just make a new one, because the p-value might be just simply biased over here. And yeah, this is another problem. The companies often report only significant changes, and so the scientific journals. And another problem is that they are dictated by the 0.05 threshold p-value. Has anyone ever heard what's the story behind 0.05 threshold p-value? Why is it used for rejecting the hypothesis? Why is it used for accepting the scientific results and so on? I hope not, because there is none. It was just picked because it made sense. It made sense for general audience, but for each research you make, you first have to make about your significance level. So what is your threshold? What can you accept from the p-value? Like what p-value satisfies you and what not? This is you should do first, and then run your analysis and experiment, because only then it's not biased towards significance threshold. And many of these problems, like conducting the research the proper way, requires more of a political will and a lot of effort. It's really hard to encourage the whole society to do it the proper way, but what we can do from ourselves is to take care of our understanding of statistics, try not to misinterpret the p-values, and I hope that this lecture will help you only a little bit about it. I'm talking a lot about the research, and maybe as a SoftServe, we are not producing lots of research, but what we definitely do is to use that research that's available. And especially in computer science, like there's a lot of research in the archive org that's not really tested in a proper way. It's only tested by people. And we use this research in our projects. So we should be double careful, maybe not at first, because there are times that you take just 25 research papers, you take every approach, you test it, you see what brings actually the results. But at some point, when producing the final results, it's really worth to read the whole process and see whether there are any like pitfalls or any mistakes and how they can hurt your interpretation of results. As a summary, I want to say some words regarding that. So some p-value misinterpretations may result in a complete fallacy. The misinterpretations may cause that you completely misunderstand the research, but that doesn't affect all the research. Some misinterpretations might simply result in stronger statements, and it's not hurtful, it's still the same direction, but it may alter your business decision if you are aware of the exact effect that is behind the p-value. And some misinterpretations may not change anything, like the experiment environment is so robust that it simply doesn't affect your interpretation. The value is here and it's trustworthy. I will repeat it all one more time. So the statistical analysis is here to help you make informed decisions. It's not to make the decisions for you. And it's so important that I figured I found a sentence that is from Neyman J. and Pearson, famous statisticians. The tests themselves give no final verdict, but as tools help the worker who's using them to form his final decision. Remember, it's just a tool. It's not an algorithm to make the decisions. Many of the misinterpretations are harmless, just like I said, in tightly controlled environments. And that can happen in computer science. Like in the computer science, we are able to set up a very robust environment, and we are very sure about each assumption that we make. And then we can misinterpret the p-value. It will still bring the same result, the same understanding of research. But it's not so sure in some more uncontrollable environments. And for example, social science, health, and based on this research, it affects our life. It affects what drugs do we take. It affects what food do we eat. It affects what do we do actually in our life and how we perceive it. And in this part, it's really very important to spread the knowledge about the p-value and to understand it the right way. What can we do to minimize the pitfalls of current practice? The first thing is carefully interpret statistical tests. Never fix on a 0.05 significance level before thinking about it for a second. Remember, first think about your significance level, what you expect from the study, what can you accept or not, and then go on with rejecting hypothesis or not. Also look at the effect size of a statistical test. Look at the confidence intervals. Look at the exact p-value. Because, for example, if you set your threshold for 0.05 and you get the p-value of 0.051, would you not reject it? It's something to consider. Critically examine all the assumptions. Going back, statistical model is much more than equations. You need to think about whole process of how the analysis was created. So examine all of the assumptions, check whether everything was right, whether, for example, the genomic studies took the equal sample of people from each race when they are comparing them. Statistically significant, non-significant results do not support the test hypothesis. This is crucial. You can reject something, but you cannot confirm something. You can confirm with your background knowledge. You can say that, in your opinion, that's right, according to all of that stuff is right, and that you wasn't able to reject this hypothesis. But you cannot say that I did the hypothesis test and I confirmed this hypothesis. No, that's not enough. It cannot be derived from statistical analysis alone. And remember, any opinion offered about the probability, likelihood, certainty, or similar property for a hypothesis because we talked about the probabilities in terms of p-value and data frequency, but for a hypothesis cannot be derived from a statistical methods alone. There has to be something more to it if someone talks about the probability. And that would be all from my side. I encourage you to start a discussion. I will be happy to answer any questions if you have, and up to my best knowledge.